Awesome. Hello, everyone. Welcome to Love Data Week. So if you haven't already checked out the rest of the programming, definitely go give that link a click. Check out all the other great sessions we got coming up. And other than that, we'll hop right into talking about one of our favorite things here at BRC, containers. Just hit the slide. Awesome. And I apologize for any jankiness in my part of the slides. Currently on my phone, so we'll do our best. Anyway, so we at Berkeley Research Computing are kind of like have a dual role on campus. So our group runs the computing cluster on campus. That's Savio. We also do a lot of work with researchers, helping them use both Savio and other computational resources available across the UC system. And so that makes us really well positioned to see a lot of the challenges that researchers and other folks across the UC system are facing when it comes to running their workflows, especially their computational workflows for their research. And what I kind of want to show you today is a pretty common problem that we see a lot of people facing. You can just hit the slide. And that's when your colleague or someone else in your research group or even yourself wants to run your software, but you have a mess of dependencies. So you have to install everything from scratch, and it still doesn't work. And now somehow those dependencies have kind of broken your other projects and they don't get the same results. And everything ends up being kind of a big mess because of how you or another user is trying to install your software. And we'll call this challenge portability. So how can we bring our software over to some other system, make it portable? Since hit slide, before you know it, when we don't make our systems portable, you end up with a bunch of SSH windows to random places trying to install the right packages, and you're not quite sure how to do it. So a lot of people will just run software on the bare metal slide. So that's kind of just running things on your basic server or laptop, straight on the hardware. So there's no segmentation between different applications. Everything is running on the same operating system. This makes it harder to do dependency management because everything's running in the same place. There's not really any segregation between different pieces of software that your software depends on. It can also be, somewhat inefficient because you have everything running in the same place. And so a bunch of smart people came up with a solution to that. They called virtual machines, which solves some of these problems. Slide. So a virtual machine is basically running a separate operating system on top of what we call bare metal. So it's kind of an abstracted layer. And so you can have a couple of different kind of mini computers running on one computer. But this has pretty high overhead, and you still have to manage the dependencies yourself. Now you can download the virtual machine as an image and kind of send it to someone else, and they can run basically the same computer wherever you want. But obviously, you don't need to send a whole computer to someone for them to run your software, right? So it's not quite as portable as we would want to run our own research software. And so what we're going to talk about today is kind of the third way to go, containers. So slide. Now, containers are basically when you can send a file to someone and they can run it exactly the same way it ran for you with minimal overhead and no setup. So it's kind of a way to code out your applications so that they run exactly the same way with a minimal performance decrease every time, no matter whose computer they're running on. Slide. So containers solve all of the problems we talked about with kind of our previous systems. Unlike running something on bare metal or even in a virtual machine, they're super portable. A container is basically kind of like a file you can just send it to someone. So it's super lightweight because they can run it on any host OS using popular, widely available tools. It's easily reproducible because it runs the same every time, because it's following the same instructions every time without any kind of like human intervention. And it's also isolated from your other processes. So you don't have to worry about dependencies clashing or different applications trying to fight for the same resources, because the container management software kind of takes care of all of that for you. Slide. So one of the tools we're going to talk about today is Docker. Docker is probably the most popular container tool out there. You'll see it everywhere, from business to research. So essentially what Docker does is take what's called a Docker file and turn this into a container that will run your software. Now, There's also another software we're going to talk about today on the next slide called Singularity. And Singularity is a slightly different tool because it's meant for scientific computing. So if you go back to your campus and you say, oh, I want to use containers on my campus's computing cluster, chances are they're using Singularity. And Singularity is a little bit different from Docker in terms of a couple of features, but you can actually turn a Docker file into a Singularity file. And so they're pretty interoperable. So with that said, let's get into like what a container is on kind of a more technical level. So what we have here is a diagram of a containerized application against applications running on virtual machines. And so the real difference is how each of these interact with the underlying physical hardware. So in a containerized application, you've got your infrastructure at the bottom. This is like the bare bones CPU, motherboard, chipset, RAM. Above that, you have your operating system, Windows, Linux, Mac. And then Docker is going to run on top of that operating system and interface directly with the kernel, as well as with your applications. And so the applications are achieving almost like near native performance, as if they were running directly on the bare metal, but you still get to keep a layer between you and the metal to keep your applications like separate and abstracted from all the craziness that might be going on in the hardware underneath. A virtual machine, on the other hand, has a guest operating system running on each virtual machine. And so rather than taking advantage of that underlying operating system, the virtual machine basically has to have an underlying operating system and its own operating system, which is a little bit inefficient and requires a lot more overhead to run. And again, isn't quite as convenient as a container for the reason we'll see on the next slide, which is that containers make configurations really simple. So this is an example of how we would run a basic web server using a popular JavaScript framework called Node. And so you can see that it's actually really simple to do. And we're going to explain kind of all the ins and outs in the future. But basically what this is doing is saying, okay, let's take an environment that's the Node 18 Alpine line. We're just going to call this like a directory app, which contains all our files, copy it in, run a script to start the server, expose a port, and that's it. We've already got a website running. And you can send this to anyone else, and they won't have to install anything other than Docker. They can just select this file, kind of hit run, and it will do the exact same thing it did on your computer, on their computer. There's no management involved, and it always works the same way every time. To get the slide, we can kind of see that there's sort of a correspondence between kind of your shell commands that you might have to run to set this up manually and the Docker file. Except unlike shell commands, the Docker file is going to guarantee that all of your dependencies are already installed. It's going to make sure that, okay, we've got the right operating system going, we've got all the right packages installed. We're going to make sure that we're running all the commands correctly. We're going to make sure we have the right port exposed, that everything kind of works. Whereas with the bash script, you're responsible for kind of ensuring a lot more of this on your own, and you can't really rely on what people have done before you. So Orion is going to kind of take us away into an example of how we can use a container in a research situation.
Okay, thanks so much, Alex. So hopefully at this point, Alex has convinced you that containers are great. They solve a lot of the problems that researchers commonly run into when they're trying to use scientific software. And generally, they're a really useful and amazing tool. But we're sort of biased on all of these counts. And there's probably a lingering doubt in your mind that if these are really such a useful tool, they must be sort of difficult or complicated to set up. And Alex showed a slide showing how easy it is to run a web server, but I would like to further entrench that point by taking an example that I've used in my research and quickly, in the course of this demo, building a Docker container, running it, and then uploading it to a high-performance computing cluster that I would actually use. So now I'm going to share screen. Can I get a thumbs up from someone? Was my screen successfully visible? Not yet.
No, I'm not seeing
Okay.
it, Orion.
Okay, there we go.
Oh, wait a
Okay.
minute.
So that should be good now. So in particular, we're going to build a Docker container that runs OpenMM, which is a simulation tool for running molecular dynamics simulations, essentially doing simulations of chemistry. And this is something that I actually spent like a long time trying to debug before switching to Docker that cost me many hours fussing around and trying to get it working for other people. And so this is an example that's very near and dear to my heart. So when we start with Docker, the first thing that we'll need to do is write a Docker file. So I'm going to go into this folder that I've set up, and I'm going to make a Docker file, and then I'm going to open it. And so we're going to create this Docker file as we go. So we now have this nice Docker file. And essentially, Docker has a few different terms that get thrown around. There's Docker files, images, and containers. And these are three different things. And I think it's worth right off the bat sort of just differentiating what they are. And the analogy that I'm going to use is it's sort of like baking a cake. And in this case, the Docker file is the recipe for the cake. There's no actual cake involved, but it is a step-by-step set of instructions for making a cake. If you follow the recipe, you will then get an image. So that image is sort of analogous to the cake itself, the physical cake. But generally, if you want to have cake, you will not eat the entire cake in one unit. Instead, you would need a slice of cake. And that is sort of the final consumable unit of cake. And the slice of cake is analogous to the container, which is what's actually running on one's machine. The difference between this analogy is that an image actually is a cake with infinite slices. There's no set number of times that you can slice it and make new containers. But I think as we're talking about Docker files, images, and containers, that's a useful analogy to keep in mind because it can get a bit confusing. So we have our Docker file now. And what we'll need to do to actually run OpenMM is we're going to use Miniconda, which is a Python tool for installing packages. We'll pull the OpenMM package from CondaForge. And if you're not familiar with Python, that's fine. Like mostly we're just trying to illustrate the different Docker commands here. But if you are, this will add a little bit more context. So we'll pull it from CondaForge. We will pull in some files that we need to run it, and then we'll actually run our OpenMM simulation in a container. So it doesn't really make sense to start from complete scratch here. The best place to start from is to actually start from a base image that we can pull from online. So let's start from a base image from Docker Hub. And Wei will talk more about Docker Hub in a little bit. But for now, what you should know is that Docker Hub is an online repository that you can pull other people's images from. So remember, that's the cake. And then we will take a slice of it. So we will use this from command. And we'll pull it from continuum IO. That's the people who have a Miniconda instance. And we'll pull down Miniconda. So what this does is it uses this pre-built Miniconda version. And that is the starting point for our Docker container. So this actually also includes like the Linux operating system and Miniconda, and we don't have to deal with setting that up ourselves, fortunately, and we can instead just start from this sort of pre-built instance. Okay, that's the from command. Next, we need to install OpenMM and one of its dependencies, GCC, which is the compiler. To do this, we will use Conda. So we'll use the run directive, which essentially runs something in bash inside of our container. And we'll use conda install. We'll specify -n. We'll specify that we want to install it in the base environment. And again, if you haven't used conda before, that's fine. We'll tell it where to get this from. In this case, we'll grab it from CondaForge, and then we'll specify that we want OpenMM. So this directive will pull down OpenMM from CondaForge and install it inside of our container. Now, there is one dependency. Because this is a container, it's, as Alex mentioned, separated from the host operating system. So while my operating system has a copy of GCC on it, which is the compiler that would normally be used. The container does not. And so we will then need to install GCC with the same syntax that we did before. And it's worth mentioning that there are other ways of, you can connect the GCC on your host operating system to the one inside the container. That's totally doable, but it's a bit out of scope for this demo. Okay, so now we have OpenMM and GCC installed, or they will be installed once we follow this recipe, inside of our container. Next, we'll need to actually have something to run. OpenMM, for all of its nice traits, can't invent simulations for you. So we're going to need to copy in some simulation files. Now let's look at this Docker demo directory and let's see what's there. I sort of cheated because I actually put the files in here ahead of time. We can look inside of OpenMM files and we can see that there's 5 files here. Most of them we don't need to care about at all. These XML files and this PDB, those are just essentially the simulation state and the information that OpenMM needs to run the simulation. We can take a very quick look at this run simulation file. Oh, here, I'll grab it. This run simulation file here, which imports OpenMM. Oh, I didn't open the right file. That's no problem. I forgot to add this as the directory. But we have run simulation right here. And what it does is it essentially imports OpenMM in Python. It loads all of these files that we talked about. It sets up a simulation, and then it runs it. And that's all we need to know, is it's a Python file that runs OpenMM using the files we have. So now we need to actually get those files into the container. And we'll do that using the copy directive. So we'll copy in our simulation files. And this is the copy directive, like everything else, it's in all caps. The first argument to copy is what is the directory that we want to copy in? And that is OpenMM files. The second argument is where in the container do we want to put that directory? And what we're going to do is we're going to create a new directory inside of our container. So our container is going to have other stuff in it. It's going to have the Linux operating system. It's going to have, or parts of the Linux distribution. It's going to have Miniconda in there. And we don't want to have this get lost in that sort of soup of directories. So we're going to create an OpenMM directory, which is where we're going to put these files. Then we are going to set the working directory. And this is more of a convenience, but as long as we're going to be jumping into our container, we might jump into where we want to be. So we're going to set the working directory to OpenMM. So we'll copy in our OpenMM files, everything we need to run the simulation. And then we will set that, essentially change directory to that directory. Okay, this next command is possibly the most confusing, but we need to tell our container how to get started. What we're going to do is we're going to use the entry point directory. What that will do is when our container starts, it will execute this command. So we're going to start a bash shell inside of our container when the container is launched. We're going to use the -c, which is like, I think, command, short for command. So we're going to use bash to execute the following command. Source, activate, base. If you know Miniconda, this will be familiar. What this is doing is it's activating the Python environment we want. And exec bash, bash. So it's going to activate the Python environment we want, and then it's going to start a bash shell in that environment. So this is how we're going to actually launch our Python environment that we want to run OpenMM in. Okay. So we have our Docker file. Our recipe is complete. We have our cake recipe. The next step is to actually make the cake. To do that, what we're going to do is we're going to call docker build -t, which is the -tag OpenMM demo. So this is the name. This is what we're going to call our image. So remember, our Docker file is the recipe. We're going to call our image openmm demo. And the dot here is signifying that it's going to happen in the current directory. So when we call docker build -t openmm demo dot, it's saying, look for a Docker file in the current directory and use that to bake a cake / to build an image. Now, much like any good cooking show, I have already done this beforehand. And so this executed very, very quickly because all of this was cached. I am pulling the cake out of the oven pre-warmed and everything. In reality, this would take a little bit longer, but we're going to ignore that for now. It's the exact same commands, it's just how long they take. So now we have a image that we've created and we want to run our image. So we're going to call docker run. This will actually take our image, slice off a piece of our image and run it as a container. This is making our slice of cake. We are cutting the cake with this command. So we're going to run docker run -it. That's just to get it to run in the terminal properly. And we're going to run openmm demo. Okay, we are now inside of the container. You can see that the prompt changed. We're in this base Conda environment, which is where we wanted to be. If you remember, we created this base environment specifically for this. And let's look at what's here. So we're also in the openmm directory. You can see here, if we print working directory, we're in openmm. And remember, we set the working directory. This is where we want it to be. We can also just take a look at the root directory and we can see that there's all of these things needed to make like Conda run and to make this Linux operating system run. But for now, we're interested in what's in openmm. This is the moment of truth because we're going to try and run this simulation just from this image that we've built. And we're going to pray that it works because that would be kind of embarrassing if it didn't. So we're going to call Python run simulation. And this will take a second to actually run because it turns out that running these molecular mechanics simulations is a bit time consuming. So to recap what we've done, we've written a recipe in this Docker file. We followed the recipe with docker-build openmm demo dot to create an image. And that image is sort of existing on a client called Docker Desktop. And I forgot to mention this at the beginning, but one small prerequisite for this demo is that you would need to install Docker Desktop first, which is like a straightforward installation from an online thing. So our openmm demo is now being hosted. It's our image exists on the Docker client, and then we're calling docker run, which grabs our image from the local Docker client and runs it. And we can see now that our simulation is indeed running successfully. So this isn't super important what's going on here, but we're stepping through time. We can get like the energy, the temperature, density, et cetera, et cetera. And we're just printing that out as the simulation proceeds. Pretty cool. Very convenient. But you might be thinking to yourself, well, that's pretty cool, but I could have done that in Conda in like 10 minutes. Why do I need to learn this whole Docker thing? What's the point of this all? And it's true. I actually wrote out what this would look like in Conda, and it's relatively straightforward, if I'm being honest. You'd have to install mini Conda, you'd have to create a new environment, you'd have to activate it, you'd have to install these packages, et cetera, and you'd have to copy things in, change directory to it, and then you could run the simulation. But if it was that simple, we probably wouldn't be running this training. And if you're remembering back to Alex's section in the beginning, there's a number of advantages over using Docker versus just running on this on the command line. First of all, maybe I have a different version of GCC that isn't compatible with openmm. That might be very hard to detect. There might be like very complicated dependencies going on behind the scenes that would make this impossible to debug. Secondly, maybe I have some issue with miniconda, some issue with global environmental variables, which are sort of the nightmare, I think, of all people who do computations, because these things can be very difficult to debug. So in theory, this likely would work, but there's all sorts of things that would cause it to fail. Further, if I actually wanted to reproduce this somewhere else, I would have to run all of these commands on that environment. Whereas with Docker, and as I'll show in a second, we can just grab our image and run it on any system. And in particular, we'll be running on Savio using Singularity, which is the technology that Alex alluded to in the beginning. So let's look through that process. Before we get too happy or too content with our usage of like Condo or whatever tools we might be using on the command line currently, let's take a closer look at exactly how easy it is to take this image that we've created locally and put it on a HPC resource. So to do that, we'll first need to go and put this on Docker Hub. So Docker Hub, I mentioned at the beginning, and Wei will talk more about it later, but it is an online place where all of the good Docker containers go to live. And in fact, I'll get this out of the way quickly. If we look back at our Docker file, when we called from, this was pulling from Docker Hub. In this case, we now want to upload our container to Docker Hub so that we can pull it down somewhere else. So we are essentially taking our completed cake, we are putting it online for anyone else to enjoy. So what we'll need to do is we'll need to create a repository. And I'm going to call it OpenMM demo 2. And it is a image for running OpenMM. Okay, and then I'm actually not going to click create because again, there's actually uploading this to online would take a little bit of time. So we're going to skip that and we're going to go to this pre-built repository that I already made. Everything else is the same except how long this takes. So let's imagine I click create repository and we have this OpenMM demo repository sitting online. We want to take the container that we've just built and upload it to this repository so that we can access it. What we'll do, and in fact this is alluded to here, is first we'll need to tag our local Docker version. So it doesn't mention this here, which is a bit unfortunate, or it says to push a new tag. So we first need to create a new tag. To do that, we'll call Docker tag, and we'll specify what image we want to tag. We want to tag OpenMM demo, and we want to tag it for this specific Docker repository. So you can see this is referencing the Docker repository. The first argument here is the local image. The second argument here is the Docker repository. So we're going to tag it online. We're going to call it latest because it is now the latest version of this container, and we'll tag it. It's a bit, nothing displays. It's a bit anticlimactic, but know now that we do have this tag in place. Then we will call Docker push. And if you've used git/github before, this is very similar to git push. But what it does is it will push our local instance that we've just tagged to the repository online. So we call Docker push Orion Cohen /OpenMM demo. And it gets all pushed. And again, the advantage of using this pre-built repository instead of a new one is that this happened in like a few seconds instead of a minute. Again, the pre-baked cooking show cake comes in handy once again. Okay, so we now have this on Docker Hub. That's great. But that wouldn't be useful if we didn't have somewhere to put it. So let's log on to Savio now. And I have this nice, what we're doing here is we're SSHing into Savio, but I have a little hack. I know I probably shouldn't show you my keys, but I'm sure you all promised not to try and remotely log into my account. And okay, we're on Savio. We're currently in my home directory on Savio, but it turns out that there's not very much space here. So we will go somewhere else. We will go to my Scratch directory where there is more space. And we now have a fresh directory. You can see that I already have this Docker demo directory set up. So we will go there, demo. And now what we'll need to do is we're going to switch tools. We've been talking about Docker this whole time, but as Alex mentioned in the beginning, the raw Docker client actually requires root privileges, root access, which is not, cluster admins would not be very happy giving root access to all of their users. So instead, we're going to use the tool Alex mentioned, which is called Singularity. It's a very similar API to Docker. And I think it's basically the same command. So we're going to call Singularity pull. We want to pull the image. We want to grab our cake down from Docker Hub, down from the clouds, cake's falling from the sky, and we want to put it locally here. So we're going to go singularity pull Docker. We're saying that we want to pull it from Docker Hub, Ryan Cohen / OpenMM latest. Oops, OpenMM demo latest. Great. And again, this is already cached because I did this like an hour ago. In reality, this would take some time to build. We've accepted that. So we now have our, what's called a singularity information file, something like that, here. And we can now run it on Savio. And I'm going to run this on the login node, which for the cluster admins in the audience are probably not happy about this, because really you shouldn't be running these simulations on the login node, but whatever. We're going to break the rules just for this demo. So we're now in the singularity container. We can look and see we have all the same stuff we had before, and we have this OpenMM repository, or this OpenMM folder here. So let's go there. We can verify that what we have inside is exactly what we had inside before. It's all the same stuff. You have state, system, run simulation, and that's what we actually want to do. We're going to run this simulation now on Savio instead of on our local machine. And it's worth mentioning at this point that my local machine is a MacBook Pro, whereas here we're running on a Linux cluster. And so there's a lot of compatibility between these two things. You can take an image built for one machine, for one architecture, and run it on another machine, which is very convenient because it means that I don't have to bother with debugging a environment on my remote cluster, which can be really annoying. Instead, I can deal with debugging things locally, and then when that problem is solved, I can just upload it to the cluster and run it. And so we can see that I'm hogging all of this login node power and running my simulation. And it's the exact same simulation that we were running before. So this is good. We have, in the course of about 20 minutes, spun up we've written a Docker file, we've written our cake recipe, we have baked our cake, we've created our image, and then we've actually instantiated that image as a specific Docker container, both locally and on a remote cluster. So that's a pretty big win. This easily, if things didn't go perfectly well, this could have taken easily a lot longer to actually run on Savio. So we're going to exit the container and now go back to the slides. Oops. Okay, here we go. So hopefully that is a good demonstration of the fact that building these containers from Docker files is not too hard. And I actually hadn't used Docker very much until a week ago as I was learning things in advance of this training. So let it be known that this can be picked up in a relatively simple amount of time. Docker is an extremely popular tool, which means that there's great documentation online. The user guide is really fantastic, and there's a lot available. Before I pass it on to Wei to cover some of the other things that Docker can do and the extensions, I should make a couple caveats. First, building and running takes a little bit more time than I showed here, and I touched on that. Second, your containers might need longer Docker files. The task that I was doing was relatively simple. It was like 5 lines. If yours take a little bit of practice, that's fine, and that's expected. And finally, running containers on HPC can be complicated. And this is a nice segue into Wei's stuff because, like, for example, I was running on a single core. How do you connect that with the multi-processing architecture? How do you connect that with GPUs? Those are questions that Wei will answer shortly.
Thank you. Thank you, Alex and Ariane. Let me share my screen now. All right, see my screen? All right, so now that you've seen Docker technologies can solve real-time, real-world problems, and you see how to build a container and image and how to run a container on the local machine and also on the Savio supercomputer cluster. Now, what's next? You might be wondering, do I need to build all the images from scratch? The answer is no. There is a plethora of public Docker images out there. So all you need to know is where to find them. However, it is always nice to know how to build a Docker image from scratch, from a definition file. For a toy image, it's not a big deal. But when you get into a real world problem application, the definition file can get really complicated very fast. So here is a really short list of Docker image repositories that are public, but some of them are private as well. Here is just a really short list that are commonly used repositories that you can just grab and use. The first one is a Docker Hub, and I will touch upon the NVIDIA NGC registry and about containers, as well as some big name cloud provider registries as well. Let me move on to the Docker. All right, this is a Docker Hub. Docker Hub probably is the largest repository in the world, including public and private owned images. So here, the Docker Hub supports images that cross on various processing architectures, such as AMD, ARM, and Windows, and basically all the basic open OS system that you can imagine are out there. For example, CentOS, Ubuntu's, and it also you can grab programming languages libraries or different kind of a data storage databases like MySQL database, things like that. You name it, they're here pretty much. And also keep in mind, when you use a Docker image, you can always modify the image based on your special demand. So here, just a quick look at the Docker Hub. So you can see the different images you can get from here: Linux, Windows, ARM, AMD, you name it, you can get it. The next one I want to show you is NVIDIA NGC repository. And this NVIDIA provides Docker images for GPU optimized applications, for example, machine learning, AI, deep learning, and also a lot of HPC applications. Just here has a really quick, you can see PyTorch, right? Widely used for machine learning, deep learning. If you can search, where is my search button? Oh, here it is. If you search for, let's say, GROMACS, right? This is a commonly used application for bioinformatics as well. So things like that, you can find images that are optimized for GPU accelerators. So we don't want to reinvent wheels, right? And there are engineers from NVIDIA, from other companies, that their job is to create optimized containers for the public to use. So why not? And the other one I want to share with you is biocontainers. I'm sure there are students, researchers in the bio field. Here you come to grab the different containers, basically for bioinformatics. So all these containers are there available for you to use. We don't have to reinvent wheels. You grab and you go. Also here, I listed a few AWS, GCP, Azure. If you use cloud computing platform, all these big name cloud providers have their own Docker image repositories that you can use. So next, now that you know where to get Docker images. So for the next few slides, I am going to show you where and how to run those images, those containers. The next few slides will be, I'm going to use a local computer, my laptop, and I'm going to show a few demos on using Kubernetes clusters. And also we'll quickly into cloud providers, several cloud providers, AWS, GCP, and as well as high performance computing clusters, such as Savio. All right, the next one is I'm going to show you a demo. I'm going to launch a Jupyter Lab container on from my laptop. As you can see, a Jupyter Lab is not really one step. You can just launch a server from your desktop, from your laptop. But if you use a container, it's just the steps of a way. So here, several commands I just listed here. First, you pull a Docker image and you run it, and then you grab the link to your browser and you launch your Jupyter Lab. Now let me switch to my terminal. Here, okay. So I have a Docker installed on my local machine. This is my laptop. I can quickly show you I have a Docker here, right? The first thing is I'm going to build a Docker image. What I'm going to do is I'm going to pull an image called a Jupyter data science notebook from the Docker Hub. And actually, this notebook has a lot of components. Typically, it would take a few minutes to build the image on my local machine. However, for live demo, we always preload everything just to save time. So it's sitting on my machine already. So I'm going to show Docker images. I'm going to show you several images sitting on my desktop. And this is the one I built actually just a few hours ago. So I'm going to run this Docker image, Docker run, and I'm going to expose. You might be wondering what I'm doing here. I am going to expose the internal port of 888 to my local machine on the port 10,000. And this is the name of the image. And now it's running. So I'm going to grab this link. If I can copy this link. All right, I'm going to open another terminal here, my web browser tab. And remember, on my local machine, I opened the port 10,000. And here, the Jupyter Lab server is running on my laptop. So you can launch, you can use Python, you can launch R, you can launch Julia. So just think about the time you saved and the quality of work you have done. It's easy. I'm going back to my terminal again. So this is a little, you pull a Docker image and you run this Docker image on your local machine. I'm going to stop this. All right, this is the first demo I want to show you. And the next one is, all right, not only, probably your local machine is not powerful enough and you want to run a Docker image from a Kubernetes cluster. So what is a Kubernetes cluster? It's an open source system that's designed to run container applications, that's designed for container application on this platform. And this Kubernetes provides the full cycle of container management and network management. scheduling, all that good stuff. If you look at the link, there's RPR Nautilus cluster, which is open to public, and you can register there. You can request resource on this cluster. And also we have internal, our group managing just recently launched internal Kubernetes cluster. It's not public facing, it's private facing. So I would have to use VPN to log in, behind the firewall. And for my current demonstration, my internet web bandwidth is not allowed. So I'm going to use the Nautilus Kubernetes cluster. So basically, I'm going to log on to the cluster, and I'm going to launch 2 Docker images. One is CentOS. The other one is Ubuntu. I will show you that those 2 containers are different. If I go here, now this is another terminal. Let me just clear this off. So you see. All right, currently I am on my terminal on the my local machine. And I'm going to show you a tool. It's called kubectl. Kubectl is a tool that is provided by Kubernetes platform. So basically, kubectl is a command line tool that allowed me to communicate from my local machine to the remote Kubernetes cluster, right? So I have a preset, my kubectl version. Well, what happened? I am on the right, okay. All right, so it is currently installed on my machine and has configured to talk remotely to the Kubernetes cluster. So I want to show you first, let me clear my screen. And in my local machine, I have several files, if you can see. So when I start another concept I need to introduce, which is a pod. So pod is the core element of Kubernetes. All right, pod is the unit that you can run one Docker image or multiple Docker image within a pod. So Kubernetes manages different pods, and different pods is just like different applications. So I'm going to start, and also, unlike Docker image, right? Docker image, you have the Docker file as a definition file, but here you use files called manifest. I'll just show you one manifest, and you can start a pod. And this is one manifest files that allow me to launch a Ubuntu pod that basically holds the Ubuntu OS. So what I need to do is kubectl. I'm going to create a pod and use this manifest file job Ubuntu. All right, you can see that this pod is created. I'm going to create another one, CentOS 7. Let me clear this again. And I'm going to show you what do I have here. Get pods. All right. So I just launched this too, right? There are 2 pods running. The other one is something the old I was testing. Now there's another command. I want to show the log files of my pod. Now you can see, hey, this pod is telling me that hello from Kubernetes. This is Docker image, and it's a CentOS Linux release 7.9. If I do Docker Ubuntu. Oh, did I? No, I didn't run. Let me see, get pods. Ubuntu is not running. Now let me delete this pod. Let me start it again. Live demo is always interesting. I'm going to delete this pod for whatever reason is not really deleted. Let me clear my screen so you can see better. I'm going to restart this pod, which is the Ubuntu. All right, create it again. I'm going to get kubectl get pods. Ubuntu is not running. Let me give it a try. Auto logs, I want to see the file. Ah, good, it's running. See here, it shows its Docker image and it's Ubuntu. And this is what I want to show you. And also, I can do, you can see kubectl get nodes. I want to show you in this Kubernetes cluster, how many nodes available for users to log on to submit their jobs. There are lots of them, right? There are hundreds of them. I'm going to clear this again and just show you one more command. Get pods. Okay. Get pods. This one. I want to see more details. Right, I want to see which node that my pod is running on. So it gives me some status, the name of my pod, and it's ready. The time of my pod has been running. This is IP address, internal IP address, and this is the node that my pod is currently running on. So this is just to give you a little sense of you can run your Docker image on a Kubernetes cluster. Now, let me go back to my slides. And also, you can run your Docker images from enterprise cloud providers such as GCP, Amazon Web Services, Microsoft Azure, you name it. They're all available. Because of time constraint, I'm not going to get into that. But as long as you have the log information, you have your account set up with all these cloud providers, you can get in to get a VM, to get a Kubernetes cluster set up and run your containers. And also you can run from HPC superclusters. Orion have showed you how to run a cluster, how to run the Docker image from a Savio cluster. And I know that UC system, different UC systems have their own supercomputer clusters set up. So as a student, you can always pick your supercluster to run your Docker image. Of course, on the cluster, you would have to use Singularity. Docker is not image because of the security reason, as Orion have mentioned. Singularity is the tool for you to run Docker images on HPC clusters. There, you can run single job, you can run multiple CPU jobs for MPI jobs, and also the GPU on GPU accelerators. So, as the last slide, here's the summary of today's workshop. Container. So container basically is a software unit that packages all the code and all the dependencies because it's a full unit. And this unit, the Docker image, is portable. So you can easily and quickly start a Docker image running from computer to computer. And because of this, it's reusable, right? You build a container once and you use it on the laptop, in the cloud, or HPC environment to produce the same result. And this is called reproducibility. It's also scalable, right? With the Docker image on Kubernetes cluster, you can launch multiple pods at the same time to run one simulation, but with the different parameters. You can run many times or running containers simultaneously. And also, the last is you don't have to build everything from scratch. You can find your image online and you grab and go. This is the beauty of using a container in different environment. So with that, this is the end of presentation. If you have any questions in the chat or unmute yourself, we're here. Thank you.